I am an engineer at VMware Tanzu / Broadcom, and I do pretty much everything Buildpacks, whether that be Cloud Foundry Buildpacks or Paketo Buildpacks. Today I'm going to talk about what it takes to make and maintain those Buildpacks and the stacks associated with them so that they're actually useful for upgrading our users' applications throughout time. I'm going to be talking mostly about cloud-native Buildpacks on this one, which I know is a hot-button topic if we learned anything this morning. So we can hop right into that. Let me start with just some quick definitions of Paketo Buildpacks and cloud-native Buildpacks. Cloud-native Buildpacks is a project that's part of the Cloud Native Computing Foundation. It defines a specification and provides a lifecycle to take in a series of build packs in an application image and output an OCI-compliant application image. Paketo Buildpacks is an open source implementation that conforms to that cloud-native build specification. So just to get that sort of all straightforward. Let's start with the easy question: what are Buildpacks and what are stacks and what do they do? Buildpacks and stacks. Stacks are a collection of two images, a build image and a run image, that are effectively the operating system that you're running on top of. We separate them out so that we can have separate concerns for the build and run sides of each image, and I'll talk about that when it comes to actually upgrading your image going forward. Buildpacks are effectively just two binaries. If you're familiar with Cloud Foundry Buildpacks, we've just removed one of the binaries. Those are build, detect and build, scan your app image, and then if they need to run, they run, and they do all of their build bits. How do they do that? Well, I've taken this from the buildpacks.io website. You take the build pack, however many that you have, run them on top of the lifecycle, which is on top of that build image that was inside of the stack. You add the app bits, you run a build, and out comes a build pack layer. I have another build pack layer, I have the app, and it's all on top of the run image. It's very important to point out here that each one of these individual chunks is distinct and independent from each other. They have no interdependencies on one another, and that will come into effect when we're talking about, once again, upgrading the actual stack. So let's get into the most important part of actually upgrading your application, which is upgrading all and maintaining all of the dependencies. Now, I've kind of slammed a bunch of metadata and stuff on here to kind of give you a flavor of the idea of how much we're trying to keep track of when we're trying to update these. Up in the top, left here, I have one of the pipeline releases, and just underneath that, all of the packages that we're talking about. And that's all just to maintain stacks. So when it comes to stacks, we actually try and release them almost as instantaneously as we can when we detect something new. We're constantly polling and checking to see if there are any updates in any of the packages that we define in either the build or the run image. And we're doing that for a couple of reasons. One, if you're building a new app, you'd probably like the latest stuff, but we also don't want to put it on a cadence because of some of the features that Cloud-native Buildpacks gives us in order to actually make our upgrade story that much smoother. On the right, we have just like a huge build pack manifest. This is just like all the dependencies that go into, this is just the Go compiler build pack. Every one of these build packs needs to have a custom way of checking the upstream for whether or not a new patch has come out. If that new patch has come out, which patch needs to go in and which patch needs to be replaced. Some of these, obviously, the upstream doesn't have a maintained artifact source, so you have to, come up with all of the logic that you need to compile the actual dependency, store that somewhere, put that stored information elsewhere. All of this is stuff that needs to be built out and built with consideration of how you actually go about upgrading it, and giving developers room to have the runway to successfully upgrade in dependencies. It's also worth pointing out for the stacks, the package lists you'll see between build and run are different. It takes a lot of consideration for us to decide, well, what packages actually need to go in. More packages need to go into build because you need more things to build out an application. But what's the bare minimum list that we can give a user so that it's actually functional? And then what's the bare minimum list that they need to actually run the application that we've done that? All of this is stuff that needs to be considered and constantly getting feedback on in terms of how we go about building out those stacks and build packs. But let's talk a little bit about the upgrade process. I've kind of teased a couple of parts of that, so let's start out with the great upgrading. It's really great, I promise. And this is rebasing. It is a function of cloud native build packs. So any application that you do that does cloud native build packs, you can rebase it. And this is where having those independent layers and that independent run image comes in. And it's why we're so obsessed with getting the run image out as fast as possible. You do not need to fully rebuild your application to upgrade your run image. You can run a Paketo, or excuse me, a pack rebase command, and it will take the image that you have, and then it will take all of the bits off the top, the app, the buildpack layer 2, the buildpack layer 1, put it right on top of the new run image, and it'll send it right out the door on its way. Doesn't need to do anything else, doesn't need to interact with any other part of the layer. And that's pretty similar to what you might see in something like Cloud Foundry as well if you were to update your stack. There we go. Or root effects, excuse me. And so that's, I think, that's the sort of purpose of why we're so, we try so hard to make sure that things get out as soon as possible, because you can actually leverage it very quickly after the new release comes out. And if you were to put that on like a release cadence or something like that, you're not actually getting as much security benefit out of that as you could. Unfortunately, you do actually have to rebuild your app occasionally, whether that be that you change things in the app, you need to upgrade it to a new dependency, whatever. But we have spent a lot of time actually trying to build out the build packs such that they make that rebuild process as short and enjoyable, however enjoyable that might be for you, as possible. So there's some stuff that's built into cloud native build packs that allows us to do some really strong work with that, and that's around this sort of idea of caching and being able to reuse layers from builds that you've done. So in your initial build, your build pack runs, it creates some build pack layers, put it on your app, that sort of thing. However, you can log metadata for layers that you used either during the build process or in the final application. This means when it comes to time to rebuild that application, what you can do is you can look through all that, you can check, and you can see like, oh, I used x.y.z version of the Go compiler. Well, I installed x.y.z in my last run. All right, great, let's reuse that layer. I don't need to go out to the internet, I don't need to re-download anything, I don't need to do anything like that. I can just push that layer right back into my build image and just use that wholesale from the previous build. Which can save, depending on your internet, a bunch of time or not very much time at all. But there's another function with these cache layers, and I've tried to illustrate that here, where you can actually save things that you've created during your build to reuse during the next build. A great example of this might be something like a Go build cache. So when you run a Go build, you get some intermediate build bits, they go into a directory, and then if you're on your local machine, when you run that build again, it can improve the build time and build reliability. All of that gets shuffled right off into a layer. Next time you run that, gets attached, and next time you run that on the same application, it gets attached, and you can just reuse that same cache in the same way. So this is where, like, I think some more of the actual discussion of making the build packs as opposed to just maintaining them gets into it. Because when we're trying to build out each build pack, we have to consider, like, what kind of things does a language family give to us? Or, like, what features does Node.js or Go or Java give to us that we could actually use to improve the build process? Is there, like, secret sauce that, like, just the community knows about, and we have to actually go and unearth and pull out of these communities in order to put it into our build packs? Is it actually applicable? Can we save these components? It's amazing how, like, some of these, like, configurations really do lead us to, like, having to, like, go to these languages and be like, hey, this very, very particular path, it seems very cool because we can do one tiny little caching thing. Is this like that? And they're like, what are you talking about to us? Like, no, we haven't considered anything like this use case. And so being able to actually then interface with them and get features to work in that way has been something that's been really interesting and rewarding. Let's talk about some additional stuff that will help you further along. And now this is where we get into the fun stuff, software bill of materials. I'm sure that everyone's been hearing about software bill of materials for, a couple of years now? And so we have that right there. It's done. I have two examples of this. The one on the left here, yeah, your left, is an example of what you can get from basically any image that you build using Paketo Buildpacks right now. So if you were to have an image and you were to go in, I think the command is pack SBOM download on any of those images, this is what you would get right now. This is the SBOM of every layer that is in that final running image. And you can see right there, we actually have a couple of different flavors, especially in like the Go target. So this is the SBOM of all of the binaries that were produced as part of a Go build. Now, let's say that you're a little bit more particular about the kind of things you would want to save. You can actually siphon even more information off using the Paketo Buildpacks on the right here. And that is during the actual build itself, you can tell the build like, hey, I need to save all of the SBOMs from all of the layers that are created at any point during this build. And that's what that is on the right there. So you can see that we actually have all of the layers that only exist during build. So that actually includes the Go compiler in there because the Go compiler isn't in the final image. It includes the Go modules because that's also not in the final image. We already used all of those to build the actual binaries. And it also includes everything that was cached as well. And so this is all stuff that's just built in, and it had to be added. And this is another sort of step in terms of like how you can upgrade your ability to do maintenance as an app developer or an operator. You actually have the log. You have the receipt of what's in there. You can scan all of these things. You can then be like, oh, I need to upgrade this because it's X out of date, or all of that sort of work. And that's sort of another consideration when we're talking about all of the things that we're trying to add in order to make sure that you can upgrade and maintain that application. So why not do it yourself? Why not either pick a different solution than this or build out your own build packs? And it's because it's a lot. There's a lot of stuff. There's 5 stacks. It'll probably be upgrading to about 9 with the introduction of Noble Numbat. You have 8 different language families, which each have a minimum of 3 different build packs inside of all of them. You have 206 different repositories across 2 different GitHub organizations, all of them running at least one action daily, and that's just going to be your Dependabot run, if not any other updates. And so it's a lot of like work just to maintain the build packs themselves. But what are they actually solving for the users? And it's that you don't have to do everything that I just mentioned in this presentation ahead of this. We have already updated your dependencies for you. We're already updating your stacks. We're already adding the SBOMs for you. You don't have to worry about getting into like a nerd fight somewhere about figuring out the best way to cache dependency. You don't have to worry about any of that. It's done. You don't have to worry about updating any Docker files. You don't have to worry about any of that. It's done. And so you can actually focus on doing something like developing an application or operating a platform, which that would be crazy, right? You don't have to get into all of these fights. And so I think that that's what I wanted to really leave with. Sometimes I think that it's hard for, at least I find it hard sometimes to always put forward the value proposition of build packs. And the value proposition of build packs is that you don't have to build them. You don't have to do my job is basically the value proposition of build packs. So I actually wanted to open up. If anyone had any questions that they would like to ask, by all means.
So what's the status or roadmap for like Paketo versus Foundry's build packs?
I am not extremely intimately familiar where the TOC is at in terms of adopting the use of cloud-native build packs into Cloud Foundry. I know that it's a very hot button issue. So yeah, for sure. One less thing for me to have to maintain, or maybe one more, I don't know. Multi-stack? Multi-architecture. Yeah, I will be talking about that. I'm doing a working group meeting update after this. But yeah, there is going to be, we are currently in the process of, and I'll get into this, we're currently in the process of supporting multiple architectures for the stack. So ARM 64, AMD 64 is hopefully on the horizon soon. Oh yeah? I'm not intimately familiar with I'm not intimately familiar with the Java build packs, unfortunately. However, if you did want to reach out to the larger Paketo community, we have a Slack channel which you can discover at paketo.io. Yeah, keep going. Yeah.
Pre-release concept. This is kind of, I'd like to stay on the lazy ways. I'd like to be able to have an upgrade story and get all the benefits of that. Maybe talk about that, like you have a new version of Ubuntu.
Yeah, once again, that'll also be what I'm talking about in my roadmap as well. Yeah, the next one, yeah. I'm on right after this as well.
He's from the future.
Yeah, absolutely. He's really planting the seeds for me. Yeah. Okay, so sorry. Sorry, I'm not sure I can hear you very well.
Okay.
Oh, perfect.
Is there any? Is this on? Can you hear me?
Yeah.
Is there any point or reason for organizations to use their own or create their own layers? Say standardize, like we have a standardized Java platform on top of the language. It seems like everyone just sort of focuses on caching bits and pieces of dependencies and things, and why not, you're doing all this maintenance of all of these different layers. All right, we don't have to worry about that, but we have our own internal stuff, and why not propagate that whole process of checking depend about it every day and doing that for like an entire organization for standardizing another layer up the stack?
I guess there's no reason why you couldn't do that. I think that the biggest issue is going to come to like what's the actual component bit size. So the reason that we've broken, so if you're familiar with the Cloud Foundry build packs, you'll know that they're pretty large and they do kind of everything all in one build pack. We've gone to a very different paradigm when it comes to Paketo build packs and cloud native build packs, because actually splitting them up into the components is where we see the best yield in terms of being able to reuse something. Because if you have to change one component, like one layer, that's the whole layer. You have to rebuild that. So you want to make those individual layers as small and customized as not customized, but as small and atomic as possible, because then that's the ability to be able to pull them back in and reuse them. Because in the example like Buildpack 1, Buildpack 2, that could be any number of things, but like one of those things that it could be is like Buildpack 1 installs a dependency that it's using, and then Buildpack 2 installs like another dependency, and if you were to have both of those parallel to each other, if either one of those, you can't reuse that layer wholesale. So that's why you would want to break it down. Now, there's not necessarily any reason why you couldn't do something like, I guess, have your own like Buildpack to install a larger like platform, but that would be what I would say is like, we don't want to get so large that you don't actually get any of the cache benefits from breaking these things up and like.
So it would make sense for an organization, not necessarily, they would have to take the approach of being granular enough on their own.
Yeah.
And end up maybe having to manage too much versus just having every build take care of itself.
Yeah. And if you're doing this just the same application in the same environment over and over again, but then I also don't know that that's necessarily the application that you're looking at for using a build pack as well.